Right. I want to get through, I want to kind of push through this stuff so you have a chance to work on things a little bit. So today, what we want to talk about is something really important in math, variable substitutions. Let's start off maybe just quickly doing just a quick example of factoring a tougher trinomial where the quadratic coefficient's not 1. What should we do there? You guys walk me through this, please. Take out the GCF. Okay, what is a GCF? Four x, yeah, good. 4x, good. Okay, so we'll take out a 4x, and then we're left with what? $17 x plus, yeah, 14. Good. Okay, so then we need to see if we can find magic numbers that work here, right? And if we can find magic numbers, then we can split and group, okay? So what would my magic numbers, which we'll call m and n, have to multiply to? 28. They multiply to the product of the outer coefficients, right? What do they have to add to? 17. They add to the middle coefficient. So what kind of a table would we make for this then? Do we want to, in the table, do we want to find pairs of potential magic numbers that multiply to 28 or that add to 17? This is one where we multiply. Because if the product is positive, it's easier to find pairs of factors. If the product is negative, then it's easier to find numbers that add to the linear coefficient. Okay? So this would be one where our table would look like this, m, n, and we're going to find pairs of magic numbers that are factors of 28 until we find some that add to 17. Okay, what would the signs of my magic numbers be in this case? Both positive. And we would just start the biggest factor we could get. We could do 28 and 1, right? Which would add to 29. Way too big. What's the next option? Yep, 14 and 2. Everybody agree? What's that add to? What's that tell us? There can't be any, right? Because we skipped them. 17 was, there's no possibility of ever getting 17. Even if there were, well, there are. I could do 7 and 4, for example. But from this point on, the numbers are going to keep getting smaller, aren't they? As the factors get closer together, the sum gets smaller. So we missed it. What's that tell us then? This is prime, right? That's our answer. Can't do anything more. Okay? All right, so for today, we want to explore this new idea. Oh, you know what? That got messed up. Holy smokes. Let's see here. What the heck happened? Okay, so sometimes complicated, doesn't have to be polynomials. This happens all through math. Calculus, we do this all the time. Sometimes complicated algebraic expressions can be written in much easier forms by just making a simple variable substitution. So the idea is we can substitute to a new variable to make things look simpler. We can do what we need to do. We can either simplify the expression or maybe we're solving an equation. So we solve, let's just say we're solving an equation. We solve the equation in the new, simpler environment, and then all we have to do is, when we're all done, is reverse the substitution and go back to the original variable. It's a great little trick, right? So let's look at this expression right here. That looks pretty complicated, right? If we're supposed to factor this big, ugly expression, yikes, that looks terrible. But maybe we can make this thing simpler. So first of all, how many terms are there in that expression? Okay, I'm getting some different numbers here a little bit, right? Okay, the answer is 3. How do we identify terms? What are terms? Right, terms are things, we'll just say for now, things that are added, which means also subtracted. Subtracting something just means you're adding a negative something, right? Does that make sense? So they would be the things that are separated by, the operation addition or subtraction, so plus or minus signs. Okay, but I see 1, 2, 3, 4 plus signs there. Not all of them really are valid if we're looking for terms. Which ones can we ignore? The ones inside the parentheses, right? Like this plus sign right here is contained inside a factor, so that's off limits, right? That one's contained inside a factor, so it's off limits. So we're really looking for the plus or minus signs that are what? Outside of any grouping mechanism, right? Outside of parentheses. Like if we had a great big square root and inside the square root was an x minus 7, that minus would be off limits because it's grouped inside the function, right? So we're looking for the ungrouped plus and minus signs when we're trying to identify the terms. So then what would those be? Well, in this case, there's an ungrouped plus and there's an ungrouped plus, right? So we end up with 3 terms. Here's the first term, there's the second term, there's the third term. Does that make sense? Okay. So what do you notice here? Well, we notice that the factor 4r plus 1 appears in 2 of the terms. Makes things look really complicated, but what do you think we could do? Substitute x for what? To make this whole thing look simpler. Yeah, 4r plus 1, exactly. Okay, so if we make that substitution, if we let x equal 4r plus 1, then what happens? Well, you can predict it makes things a lot easier, right? Then all those 4r plus 1s just get replaced by x's, and look how much simpler that expression gets. Right? Pretty simple. Now all we've got to do is factor that. Well, what magic numbers multiply to 16 and add to 8? Positive 4 and positive 4, right? So we end up getting this factors into x plus 4 quantity squared. Are we done? How come? Because the original expression was written in terms of r, not x. So now we made the substitution, which allowed us to, it gave us a much simpler expression, easily factorable. Now that we're done with the whole process, we just reverse the substitution to get our final answer. So where we used to have an x, we're going to trade that for a 4r plus 1, which is why every time you make a variable substitution, you always put a box around it because you're coming back to it probably to reverse the substitution at some point. There are some rare cases in calculus where if we're doing definite integration or something, we can just, we can do some tricks and avoid having to reverse the substitution, but we'll talk about that in 2 years. Okay, so then we end up with, if we reverse this, here, let's look at this real quick. So what do we get here then? Oops. So this would equal where I used to have an x, I'm going to make those brackets now. That x is getting replaced with a 4r plus 1. I'd be tempted to put that in parentheses. Do the parentheses really accomplish anything there? They don't, right? So I'll just leave it out. Plus 4 quantity squared, and look what I can do. I can simplify inside those groups. Here, I'm going to do this real quick. I'm just going to do that. We can remove those parentheses though, right? And we can just turn that into 4r plus 5. And then I could change those brackets to parentheses to make things look simpler, right? I only have one layer of grouping symbols, so make them the simplest, which are parentheses. Again, oftentimes technology won't recognize brackets. You have to group parentheses and then outer parentheses, which is just visually a little harder to navigate. But like in Desmos, for example, I don't think it'll let you do brackets. Brackets mean something else. Bracket means like a vector or a list, and so it will interpret it incorrectly. Most technology does that. When you include things in brackets, it's assuming you're giving it components of a vector, right? So you just have to use nested parentheses. Okay, give me thumbs on that though. Does that make sense? Okay. All right, what about that one? Can you guys suggest? I mean, that looks somewhat complicated because it's a quartic polynomial instead of, quartic trinomial instead of being a quadratic trinomial. But it's easier to factor quadratic trinomials, right? So anybody have any ideas about a substitution we could make there that would make this simpler? So, okay, so we want to substitute something for x squared. We need a different variable though, right? I couldn't use x for x squared. That wouldn't make sense, right? I have to pick a different variable than x, so like y or something, right? Yeah, did everybody get that? What's the giveaway here that we want to make a substitution? And in this case, we'll just call it y. We'll let y equal x squared. What's the giveaway up here that kind of tells us for future reference where you'll be able to recognize that? What about the exponents kind of gives that away? Yeah, they're even numbers, right? So they're both divisible by 2. It makes sense? Okay. So if we make that substitution, well, look, then we get a simpler looking polynomial. It's a quadratic trinomial instead of quartic. And so we could potentially solve this. I can't factor out a GCF, right, or potentially factor it, not solve it. If I am going to factor this, I'd have to find magic numbers. What would they have to multiply to? Negative 210, right? The product of the outer coefficients. And they'd have to add to what? 29, good. The middle coefficient. Okay, so what kind of a table would we make here? Do we want pairs of numbers that multiply to negative 210 or pairs of numbers that add to 29? Add to 29 because of the product is negative, okay? So we'll find pairs of numbers that add to 29, but then we'll make sure that we identify some that multiply to negative 210 if they exist. So I'll get you started. What's bigger, the positive or the negative? Obviously, we have to have one of each, right, because they multiply to a negative. Positive is bigger. It has to be, if I started at 29, I'd get 29 plus 0. That wouldn't make sense, right? 0 isn't negative. I need to pick the next, I need to be at least one higher than what the sum is. So like 30 and negative 1 would add to 29. But they multiply to negative 30, which is way too small, right? So we want to jump up the list a little bit, like, I don't know, what do you think, like 34 or something? 34 plus what is 29? Negative 5. What's 34 times negative 5? Okay, so which direction do I have to go on my list? I got to go down in this case, right? I got to get bigger values of m. Okay, so what do you think? You throw one out. 36, okay. So 36, and that would be what, negative 7? Oh, that looks too big, doesn't it? Everybody agree? It's a negative too big a number. So what's my only possibility? 35. 35 and negative 6. What's that give us? It's 35 times negative 6. Oh yeah, negative 210, isn't it? Okay, that's our winner. Okay, so we got our magic numbers, right? What do we do with them? What was the point of finding those? Okay, good. So that's where we're going to split the middle term. So this is the splitting process. Our goal is if we can find magic numbers, we use them to split the middle term. So that gives me 4 terms, and so I can factor by grouping, right? Okay, so now this is kind of my OCD math brain here. I am super unorganized about most things in my life. I just asked Mrs. Oya. My garage is way too disorganized. But when it comes to math, I am very organized because I know how important it is, right? So take it or leave it here, but what I would do here when I'm splitting that middle number into a positive and a negative, I would always put the negative first. Is this a make or break issue? Not really, but I think it makes things a little bit easier. So I'm going to put the negative 7 and then the 36. So what should I write here? Negative 7. Oh, negative 6. Whoops. Is it just negative 6? Why? Because I'm splitting that whole term, right? I'm splitting the 29y's into negative 6y's plus 35y's. And then the other terms remain the same. Why would I put the negative 1 first? Do you see any advantage to that? Okay, so it makes, first of all, it makes the first term of the second group positive, right? Which is a little bit more convenient. And then I can also just circle that plus sign to split it into my groups. Does that make sense? Is it a huge deal? No, not really, but it helps a little bit. Okay, so if we split this then, well, we did split it. What do I get from my first group when I factor it? What's my GCF? Just a y. What's left behind? Oh, by the way, before we even jump into this, should I check to see if factoring by grouping is even going to work with my tests? You're right, Ben. How come? If I find magic numbers, it's guaranteed to work, right? You don't even have to bother. You know you're going to have success. Okay, so what's my leftover again? 5y minus 6 plus, where do I build the second group? How do I build the second group? Good. The first thing I'm always going to do, remember, is I'm going to start with the leftover and then determine the GCF. Well, what would it have to be? Yeah, it'd have to be positive 7. Good. And so what do we get for our answer? There we go. Good. We'll factor out the 5y minus 6, which leaves behind y plus 7. Good. We done? Oh, what do we have to do? Yeah, we got to reverse the substitution. Good. So we need a box around that. We're going to swap the y's for x squareds, and we get the final answer, 5x squared minus 6 times x squared plus 7. Good? Okay, Good, good. All right. Okay, so when you're factoring trinomials by grouping, and we're only using a single variable, it's just more convenient for us to focus on the magic numbers only, right? Just the coefficients. But we can include the variables. I just want to show that to you, and then I'm going to show you a case where it's important that you do include the variables. So what I mean by that is there's no GCF. What would m times n have to multiply to if I include the variables? Not just the numbers. It becomes, now instead of just the product of the outer coefficients, it becomes the product of the outer terms. So 5x squared times 7 gives me 35x squared, yeah. What would the magic numbers have to add to? Negative 12x. Now they add not just to the middle coefficient, but the middle term. So what would the signs be then of the terms? They'd both be negative, and I bet you guys can jump right to this. What would they be? What two terms would multiply to positive 35x squared and add to negative 12x? Negative 7x and negative 5x. And from that point forward, does it change anything? No. At this point, we're going to split that middle term into negative 7x minus 5x, and we won't even do this problem from this point. But now I would just factor that by grouping. Now it's exactly the same process as if we had only included the coefficients. Okay, makes sense? That's a little bit tougher though, agreed? I mean, the way we did it before is a little simpler. Okay, but why would I show that to you? Because what about a problem like this one? When you have multiple variables, if you're stuck factoring a trinomial that includes multiple variables, it is way easier to include the variables. Okay, so let's try this one. Now, what's my GCF? (10x) it looks like, agreed? Okay. What's left behind if we undistribute a 10x? Z good plus okay. Let me make a suggestion here. Charlie, you see maybe a variable substitution that might be helpful? Yeah, y squared. Something for y squared. Let's call it u. Okay, good. Okay, that's going to help a little bit, isn't it? So now we're going to get, we've got our 10x out front. This is going to give me 4 times, what's y to the 4th going to convert to if I change to u? What, u equals y squared. U squared. Minus what? Okay. So now I've got multiple variables in that quadratic trinomial. Okay. What would my magic numbers have to multiply to this time? For u squared, z squared, everybody agree the product of the outer terms? what would my magic numbers, my magic terms, I should say now, have to add to? Yeah, negative 4uz. So what would they be? What would my magic terms be? What terms would multiply to positive 4u squared z squared, but add to negative 4uz? Everybody agree? Okay. So I can just split that middle term then into negative 2uz minus 2uz, and everything else stays the same. Okay, now what? Inside the brackets, what would I do? Yeah, first group, so I'm going to put a circled plus sign there. First group, what's my GCF? What is it again? 2u, yep. Times what left over? Plus, I've got to have the same leftover, right? And so what GCF would I need for group 2? And then don't forget, I've got my 10x out front, right? Okay, so now what factor could I undistribute out front with the 10x? 2u minus z. Everybody see that? Leaving behind what? 2u minus z. Okay, so I could simplify that. What's that give me? Yeah, so I get 10x times the quantity 2u minus z squared. Perfect. Are we done? What do I have to do? Reverse the substitution. U just equaled, what was it, y squared? Y squared. Okay, so then we end up with 10x times 2y squared minus z quantity squared. And we got it. Make sense? Do you see how much easier that was? I promise you, this would be a little bit confusing if you tried to do this without including the variables. It gets a little bit, I mean, you can do it, but it's a little bit tricky. It's much easier if you have multiple variables in your trinomial. It's much easier to just include the variables and establish magic terms instead of magic numbers. Okay? Give me thumbs on that. Does that make sense? Okay. I think, yeah, we don't need to do that one. Okay, so I got a little logic puzzler for you can think about. I'll let you work, but I'm going to talk you through this. This is kind of a good one. Believe it or not, this actually is the kind of thinking you would do in digital circuit design using gates, like, you know, AND and OR gates and NAND and NOR gates and XAND gates and all that stuff, right? XOR gates. So you're visiting the land of logic, home of the city of truth and the city of lies. All residents of the city of truth are truth tellers who always tell the truth. So there's a logic rule, okay? While all residents of the city of lies are liars who always lie, another logic rule. You are trying to get to the city of truth, of course, but come to a fork in the road. You know that one fork leads to the city of truth and the other leads to the city of lies, but you're not sure which fork leads to which place. A guard stands at the fork, but you don't know if he's a liar or a truth teller. You have permission to ask the guard one question only. That's it. What question could you ask to ensure that you end up in the city of truth?